All right, this is video 2.5. I forgot to put this one on one of the slides, so I really wanted to get to it though. This is a very unique type of problem, and it really steps the game up a little bit with related rates. So everything we've seen so far has been very relatable in terms of, Pythagorean theorem or circles or volume equations. And here in example number 7, things get a little bit more difficult. So you'll see on the right hand side you have a diagram of a rocket that is flying vertically. And over here is located a camera exactly 2,000 feet from the launch pad of the rocket. And as the rocket goes up in the air, the angle between the ground and the site of the camera is increasing. And the question that we're trying to find the answer to in this problem is, what is the rate of change of the angle of elevation of the camera 10 seconds after liftoff? So I want to know how this angle is changing as it follows the rocket up into the air. So clearly it was focused here at one time and then started to follow the rocket up. And we want to find out d theta dt. So I'm going to write that down. I want d theta dt. And there's a reason why I'm writing it down first. This is a triangle, and you'll see a lot of triangle problems, and you're going to have to make a determination. Are you looking for area of the triangle, in which case you would use 1/2 base times height? Are you looking for the relationship of the sides of the triangle, in which case you're going to use the Pythagorean theorem? Or in this case, are you looking for something about the angles in the triangle? And if you're looking for angles in the triangle, you're not going to use area, and you're not going to use Pythagorean theorem. You're going to have to use a trig function. So what I have is I am looking for my d theta dt. So I'm looking for the rate of change of this angle. And there's a couple of other things that are given in the problem. One of the first things that's given in the problem is that s is equal to 50t squared. That the position of the rocket is given as 50t squared. Well, I'm going to write that over here, but I'm just going to kind of write it as, y equals, because it's really just a y variable. So y equals 50t squared. I also know that 2,000, the distance the camera is from the launching pad, is constant in the problem. So that's not going to change. So my x value is 2,000. What I don't know is anything about the hypotenuse. I could find some information about the hypotenuse, but the unique thing about this hypotenuse is the hypotenuse is growing as theta is changing. So as that rocket goes up in the air, the hypotenuse is changing as well. I don't have any information about dz dt, or the rate of change of the hypotenuse, so I really don't want to use it in my problem. And as you look at what I'm not what I'm given, but what I've kind of surmised over here, I'm given some information about y and x, and I'm looking for information about theta. So it would then make sense that in terms of the equation I use an equation that relates theta, y, and x. Well, that's tangent, folks. So tangent theta is equal to y over x. Remember, x is going to be constant. So that x in the denominator, although it looks like we may be using the quotient rule at some point, is really not. It's really that tangent theta is equal to y over 2,000. So I didn't need to worry about dx dt, because dx dt is 0. There is no change. And I'm going to need some information about dy dt, because when I go to take a derivative here, I'm going to need to know dy dt. Well, that brings us back to this little equation over here, that y is equal to 50t squared. So if I want to find dy dt, I just take the derivative with respect to t of 50t squared. And the derivative with respect to t of 50t squared is 100t. So although dy dt isn't explicitly given to me in the problem, I am going to take the time to say, okay, my dy dt that I know is 100t. And again, I'm interested specifically at when t is equal to 10 in my problem. So now I have an equation that I can take the derivative of. I know that when I take that equation, I'm going to get what I'm trying to find. I'm going to get a d theta dt somewhere, and I'm also going to generate a dy dt, which I also know. So that's good. I have everything that I'm going to need. So I'm going to draw a little triangle here. I'll be back in just a second. So I'm going to pause this and draw a triangle, and then we'll talk about it. All right, so let me take a shot at explaining to what I just did over here in the bottom right-hand corner. So if t is equal to 10, then I know that 50t squared would be 50 times 100, which would be 5,000. So the height at t equals 10 of the rocket is 5,000. The 2,000 is set permanently as the distance the camera is away from the launch pad, and then the hypotenuse of this right triangle would be the square root of 29 followed by 60. So what's that? Thousands, million, 29 million. So 29 million. Well, a similar triangle to that, if I were to simplify and look at dividing through by 1,000, would be a 2, 5, radical 29 right triangle. So keep in mind this is theta. This is the relationship in the triangle that I'm dealing with my rocket. Okay, so that's going to come into play in just a second. So now we're going to get into just doing the related rates piece. I am going to take my tangent theta equals y over 2,000 equation and take the derivative of it. So when I take the derivative of tangent theta, I get secant squared theta d theta dt. Don't forget about the d theta dt. We need it. That's what we're looking for. Secant squared theta d theta dt. And then remember the 2,000 is really 1/2000th. So it's 1 over 2,000 times the derivative of y, or dy dt. I want to find d theta dt. So d theta dt is equal to dy dt divided by 2,000 secant squared theta. And I'm going to need some more work room, so I'm going to copy that onto the next page, and then we're going to work it from there. Alright, I'm back. So there's my right triangle, my 2, 5, radical 29 right triangle. There's my related rates equation. I have dy dt divided by 2,000 secant squared theta. Secant squared theta. If only I knew what secant squared theta was. Oh wait, I do know what secant squared theta is, because secant squared is just the reciprocal of cosine squared. So if I come back over here to my triangle, I know cosine theta is 2 over radical 29, which means that secant theta is radical 29 over 2, and secant squared theta is 29 over 4. So I can take and use that information in my problem. So let me go back over here. I have d theta dt is equal to, now dy dt, I also knew that. dy dt was 100t. So 100t at t equals 10 would just be 100 times 10. So 100 times 10 is 1,000. So I have 1,000 divided by my 2,000 from my original triangle times 29 over 4. And look, now I'm down to just evaluating this and getting a numeric value for it. So d theta dt, you can double check my math here, but these zeros are all going to cross out, and I'm left with 1 over 2 times 29 fourths. So that would be 1 over 29 halves, and 1 over 29 halves is just 2 over 29. So d theta dt is 2 over 29. Remember, calculus is always done in radians, so this is radians, and the time was seconds, so radians per second. So that is the rate of change of the angle theta following the rocket up in the air. There's a lot there. You're going to have to do another 1 or 2 of these before you become comfortable with them, but it's just another triangle problem that you have to look at differently to build the angular stuff in there to get your d theta dt. Okay, so I wanted to show you that one. Hopefully everything is going well. Hopefully I'm doing well. I don't know. It's Monday night right now, so I haven't had my surgery yet. So hopefully everything will be going well for everyone. All right, I will talk to you guys again later.